You know, if I were to tell you that you're not really here, that the chair you're sitting in, the screen you're watching, even the atoms that make up your body don't have definite properties until the moment you observe them, you'd think I'd lost my mind. And yet, that's precisely what quantum mechanics reveals. Not as speculation, not as philosophy dressed up in equations, but as the most rigorously tested, experimentally verified description of nature we've ever created. The paradox isn't that reality behaves this way. The paradox is that we ever believed it could behave any other way. Let me begin with something that sounds like a contradiction, because in physics, as in life, the opposite of a correct statement is a false statement. But the opposite of a profound truth may well be another profound truth. Consider the electron. Ask a physicist what it is, and you'll get two answers that cannot both be right according to classical logic. It's a particle, a discrete, localized point with definite position and momentum, and is a wave spread out through space, exhibiting interference patterns without any definite location at all. Both descriptions are experimentally verified. Both are essential for making predictions. Both are incomplete. And here's what matters. This isn't a failure of our knowledge. This is a feature of reality itself. I spent decades trying to make sense of this, and what I discovered wasn't a way to resolve the contradiction. It was that the contradiction is fundamental. We call it complementarity. Wave and particle aren't two aspects of some deeper hidden reality that we simply haven't discovered yet. They are the only two descriptions we have, and we need both, even though applying both simultaneously produces nonsense. The electron doesn't secretly know whether it's a wave or particle and then trick us depending on how we measure it. Rather, the very question, which is it really, has no meaning. Reality at the atomic scale doesn't contain an answer to that question, because the question assumes something that isn't there, a classical object with definite properties independent of observation. Now, I can see you wanting to object. Surely you're thinking, the electron must be something when we're not looking at it. Surely it has a position, a trajectory, properties that exist whether we measure them or not. This is the intuition we carry from everyday life, where objects behave predictably. You close your eyes, the table doesn't vanish. You turn away from the moon, it continues orbiting. Classical physics, Newton's physics, is built on this bedrock assumption. Things have properties, and measurement simply reveals those properties without changing them. The thermometer doesn't alter the temperature of the room. The ruler doesn't modify the length of the table. Observation is passive. But here's where everything changes. At the quantum scale, observation is not passive. It's creative. Not in some mystical sense, but in a precise mathematical, experimentally verifiable sense. Or the act of measurement doesn't reveal a pre-existing property. He brings that property into existence. Before measurement, the electron doesn't have a definite position. It exists in what we call a superposition, a state where it simultaneously occupies multiple positions, multiple states, governed by a wave function that describes probabilities, not certainties. The moment you measure, the moment you interact with that system in a way that extracts information, the wave function collapses. Suddenly, the electron has a position, not because you discovered where it was, because the act of observation forced it to choose. Let me show you what I mean with the experiment that haunts every physicist who truly grasps its implications. The double-slit experiment. Imagine a simple setup, a source that emits electrons one at a time, a barrier with two narrow slits, and a screen that detects where each electron lands. Fire an electron toward the barrier. Common sense says it goes through one slit or the other, like a bullet through a gate. Run the experiment thousands of times, and you would expect two red bands on the screen, corresponding to the two paths. That's what particles do. But that's not what happens. What you get instead is an interference pattern alternating bright and dark bands, exactly like what you'd see if waves were passing through both slits simultaneously, overlapping, reinforcing in some places and cancelling in others. Even though you're sending one electron at a time, even though each electron arrives at the screen as a single discrete impact, send enough of them and the pattern emerges, wave-like interference from particle-like objects. Both descriptions are needed. The electron interferes with itself, as if it traveled through both slits at once, spreading out as a wave. Yet it always arrives as a localized particle. Now here's where it gets strange and where classical thinking shatters completely. You might think, let me just check which slit the electron actually goes through. Put a detector at each slit, something that registers whether the electron passes. Do that and the interference pattern vanishes completely. You get two bands, exactly what you'd expect from particles choosing one path or the other. The act of observation determining which slit the electron traverses changes the outcome, not because you disturbed it with clumsy apparatus, not because your measurement was imprecise, but because asking which slit did it go through forces the electron to behave as a particle with a definite trajectory, and that very act destroys the wave-like superposition that creates interference. You see the problem now. If you observe, you get a particle with a definite path and no interference. If you don't observe, you get interference and no definite path. You cannot have both. And this isn't a limitation of technology or experimental skills, this complementarity written into the fabric of nature. The electron exhibits particle behavior or wave behavior depending on the kind of measurement you perform, and you cannot design an experiment that extracts both kinds of information simultaneously. Nature forbids it. The mathematics bears this out with ruthless precision. Then Heisenberg showed that certain pairs of properties cannot both be known with arbitrary accuracy. Position and momentum, for instance, are complementary in this technical sense. The more precisely you measure where an electron is, the less you can know about how fast it's moving. This isn't measurement error. It's encoded in the structure of quantum mechanics, the uncertainty principle, the product of uncertainties in position and momentum as a lower bound set by Planck's constant. You can squeeze the uncertainty in position as small as you want, but momentum uncertainty balloons proportionally. Not because your instruments aren't good enough, because the electron doesn't have both properties simultaneously with unlimited precision. Reality itself is blurry at this scale. And here's what people often miss. This isn't about particles being tiny and hard to pin down. It's about the breakdown of classical concepts. Position and momentum are ideas we borrowed from the macroscopic world, where objects have locations and speeds that exist independent of measurement. We assumed these concepts applied universally, that an electron was just a very small version of a billiard ball. But electrons aren't small billiard balls, they're quantum objects. And quantum objects don't behave like scaled-down classical ones. Our language was built for the world of tables and chairs and planets objects that have definite properties whether we look or not. When we try to apply the language to electrons and photons, it breaks. Not because we're being imprecise, but because the concepts themselves don't map onto quantum reality. So what replaces them? The wave function. This is the mathematical object that describes a quantum system and is genuinely strange. Before measurement, an electron isn't here or there. It's described by a wave function that spreads through space, assigning probabilities to different outcomes. The wave function contains all the information you can have about the system, but that information is fundamentally probabilistic. You can predict the odds of finding the electron in various locations, but you cannot predict with certainty where it will be. Even with perfect knowledge of the wave function, even with infinite computational power, you cannot do better than probabilities. The randomness isn't ignorance. It's built into nature, and when you measure, the wave function collapses. Instantly, all those probabilities condense into a single outcome. The electron is found here, not there. The moment of measurement is a moment of creation, not of the electron itself, which existed in some form before, but of the definite property you're measuring. Before you looked, where is the electron? Didn't have an answer. After you look, it does. That's not philosophy. That's what the mathematics describes, and is what every experiment confirms. Now, you want to ask, what's the wave function made of? Where does it exist? What is it really? And here I have to tell you, these questions assume too much. The wave function isn't a physical wave rippling through space like water or sound. It's a mathematical description of what we can know. Asking what it's made of is like asking what color Wednesday is. The question doesn't make sense because it smuggles in classical assumptions that don't apply. The wave function lives in an abstract space, Hilbert space. if you want the technical term, and it evolves according to Schrödinger's equation in a perfectly deterministic way until measurement. Then it collapses, probabilistically, giving you an outcome. This is complementarity again at a deeper level. You need both pictures, the deterministic evolution of the wave function between measurements and the probabilistic collapse during measurement. Both are essential. Neither alone captures the full story. Classical physics told us, here is the state of the system, here are the laws, now you can predict the future with certainty. Quantum mechanics says, here's the wave function, here are the laws, now you can predict the probabilities of different futures. The shift from certainty to probability isn't a bug. It's what nature allows at this scale. And before you think this is just theoretical abstraction, let me ground you in reality. Every computer chip in the device you're using right now relies on quantum tunneling, a phenomenon where electrons pass through barriers they classically shouldn't be able to cross because their wave function doesn't go to zero at the barrier. It leaks through. Transistors, the building blocks of all modern electronics, exploit this. Lasers work because of stimulated emission, a purely quantum process. MRI machines map the interior of your body by manipulating the quantum spins of hydrogen nuclei. Atomic clocks, which keep GPS satellites synchronized to within billionths of a second, work because electrons transition between energy levels with exquisite precision energy levels that only exist because of quantum mechanics. This isn't speculation. This is engineering. This is the backbone of the technology you rely on daily. The Copenhagen interpretation, this framework I helped develop, has been tested billions upon billions of times. Every prediction it makes about interference patterns, energy levels, transition probabilities has been confirmed. Not approximately, exactly. To astonishing precision. If quantum mechanics were wrong, your phone wouldn't work. Semiconductors wouldn't function. Chemistry would be incomprehensible because chemical bonds are quantum mechanical. You could explain why atoms are stable, why they emit light at specific wavelengths, why matter has the properties it does. The entire edifice of modern physics rests on this foundation, and it holds. Yet it demands we abandon cherished intuitions. The idea that objects have definite properties independent of observation. Gone. The idea that you can, in principle, measure everything about a system with arbitrary precision. Gone. The idea that the universe unfolds deterministically from initial conditions. Gone. Replaced by probabilities and possibilities that crystallize only when observed. And here's the deepest lesson. This isn't a temporary state of ignorance waiting to be resolved by a better theory. Einstein thought so. He famously said, God does not play dice. He believes quantum mechanics was incomplete, that there must be hidden variables, deeper properties we simply haven't discovered yet, that would restore determinism and objectivity. But experiments have ruled that out. John Bell formulated a way to test whether hidden variables could reproduce quantum predictions, and the experiments came down decisively. No local hidden variable theory can match what quantum mechanics predicts and what experiments observe. The randomness is real. The lack of definite properties before measurement is real. You cannot restore classical intuition without violating experimental facts. Nature, at its core, is genuinely probabilistic and observer-dependent in a way that cannot be explained away. Does that mean consciousness creates reality? No. That's a misunderstanding that plagues popular accounts. The observer in quantum mechanics isn't a conscious mind, it's any interaction that extracts information, any process that entangles the quantum system with the environment in a way that destroys superposition. A photon hitting an electron and scattering counts as observation. A dust particle interacting with an atom, consciousness, has nothing special to do with it except that conscious beings happen to perform deliberate measurements. The key is interaction, not awareness. But here's what is true, and it's just as profound. You cannot separate the observer from the observed. In classical physics, you could imagine standing outside the universe, watching it unfold according to objective laws, your presence irrelevant. In quantum mechanics, that's impossible. Every measurement you make is an interaction that changes the system. The properties you measure don't exist independently of the measurement process. There is no view from nowhere. We are not spectators looking at nature from the outside. We are participants embedded in the physical world and our interactions with it are part of the story. This is why I always insisted on careful language. When students would ask, what is the electron doing between measurements, I'd say, the question assumes too much. You're imagining the electron as a little ball traveling along some path you're just not privileged to see. But that big trajectory, path, position at every instant, is a classical concept. It doesn't apply. The electron between measurements is described by a wave function, and the wave function doesn't encode a hidden trajectory. It encodes potentialities, not actualities. The electron isn't secretly somewhere doing something. It's in a superposition of possibilities. And only measurement collapses that into a single reality. This sounds mystical, I know. It sounds like we're saying reality isn't real until we look. But that's not quite it. Reality is real quantum mechanics, describes reality with extraordinary accuracy. What's not real, in the classical sense, is the assumption that objects have all properties at all times independent of context. That assumption worked beautifully for cannonballs and planets. It fails for electrons and photons. The lesson isn't that reality is subjective or illusory. The lesson is that reality is contextual. What you can know about a system depends on how you interact with it, and those interactions are mutually exclusive. Measure position precisely, you lose information about momentum. Measure which slit the electron went through, you lose the interference pattern. Both descriptions are real, both are needed. Neither is complete. And this brings me to the question I'm asked most often. Does quantum mechanics mean free will exists, or does it disprove it? And I have to say, I don't know. Quantum randomness means the future isn't deterministically fixed by the past. There's genuine openness, genuine unpredictability. But randomness isn't the same as agency. A dice roll is random, but it's not free will. Whether the indeterminacy at the quantum level somehow enables conscious choice is a question quantum mechanics doesn't answer. It changes the terms of the debate. You can't be a strict determinist if quantum mechanics is true, but it doesn't resolve the puzzle of consciousness and volition. What it does show is that the universe is stranger, more subtle, more resistant to our intuitions than we ever imagined. We thought we could describe nature in the language of everyday objects, just scaled down. We thought measurement was passive, that observation didn't alter what we observed, that properties existed objectively out there waiting to be discovered. Every one of those assumptions turned out to be wrong, not slightly wrong, fundamentally wrong. And yet, by abandoning them, by accepting complementarity and uncertainty and the active role of measurement, we built a theory that works, that predicts, that explains, that powers the technology of the modern world. So when I say you're not really here, I don't mean you're imaginary. I mean that here is not as simple as it seems. The atoms that make up your body don't have definite positions and velocities until interactions pin them down. And those interactions are happening constantly, trillions upon trillions of times per second, collapsing wave functions, creating the stable, definite world you experience. At the macroscopic scale, quantum effects average out. Superpositions become so fragile, so sensitive to the environment, that they collapse almost instantly, and you're left with the appearance of classical behavior. The table looks solid because the quantum uncertainties in its atoms are so small compared to its size that they're invisible. But underneath, at the deepest level, the same quantum rules apply. You're not really here in the sense that the atoms composing you don't have the definite objective properties classical physics promise. They exist in a web of probabilities or potentialities, constantly collapsing into definite states through interaction with the environment, with each other, with the photons bouncing off you into my eyes. You're real, but real means something different than we thought. It means contextual, participatory, observer-dependent, in ways that classical language struggles to capture. And perhaps that's the deepest lesson of all. Physics has given us extraordinary power to split atoms, to manipulate light, to engineer the quantum world. But it has also shown us the boundary of what can be understood using classical concepts. There are questions we can't answer not because we are ignorant, but because the questions themselves assume too much. Where is the electron when we are not looking is such a question. It assumes a world of definite properties independent of observation. and that world doesn't exist at the quantum scale. Does that mean we've reached the limits of knowledge? No. It means we've learned to ask better questions. Instead of where is it, we ask what's the probability of finding it here. Instead of what is it really, we ask what can we measure and how do those measurements relate. And those questions have answers: precise, testable, extraordinary success instead of extraordinary success or answers. Quantum mechanics doesn't tell us everything, but it tells us what we can know, and it tells us why some things cannot be known. That's not defeat, that's wisdom. I spent my life trying to understand this, trying to articulate it, trying to find language that could bridge the gap between classical intuition and quantum reality. And what I learned is that you can't eliminate the gap. You can only acknowledge it, work with it, use complementary descriptions that contradict each other, but together approach the truth. Wave and particle, position and momentum, deterministic evolution and probabilistic collapse, both sides are necessary. Both are incomplete. And that's not a flaw in our understanding. That's the structure of nature itself. So if you're not confused, you haven't understood it properly. If this sounds strange, unsettling, even impossible good, that means you're grappling with it honestly. The quantum world doesn't fit our intuitions because our intuitions evolved to navigate a macroscopic world where quantum effects are invisible. But once you let go of the demand that reality conform to those intuitions, once you accept complementarity and embrace the role of observation, a new picture emerges. Not simpler, not more comfortable, but deeper, truer, more in line with what experiments actually show. And in the end, that's all we can ask. Not that nature makes sense according to our preconceptions, but that we have the humility, the courage, and the intellectual honesty to follow the evidence wherever it leads, even if it leads to a reality where you are not really here, at least not in the way you thought.